Welcome to the deep dive. So today we're looking at something that, honestly, I think we all take for granted. We've got an incredible piece today by Aaron Rose.
Yeah, the technology writer and software engineer, right?
Exactly, yeah. It's an article from tech-reader.blog, and it's called The Secret Life of Python, Deconstructing the Hello World Program.
Which is such a great title, honestly.
It really is. And our mission today for you listening is to basically completely shatter a very common illusion. We're going to uncover the massive, just hidden machinery operating right beneath the surface of literally the absolute simplest line of code anyone can write.
Right, because we just take that simplicity as a given,
Yeah.
It's a really fascinating undertaking because we are literally going to trace the entire microscopic universe that basically spins up the exact moment you press enter on a basic script.
Okay, so think about it like walking into a dark room and flipping a light switch.
Oh, that's a good way to look at it.
Right. You just flick this tiny piece of plastic on the wall and boom, the room instantly floods with light. To you, it's just one single, simple action.
At the flick of the wrist.
Exactly. But if you were to, I don't know, tear down the drywall right then and there, you'd find this incredibly complex, hidden infrastructure. I mean, we're talking circuits, breaker boxes, miles of underground cabling leading out to some massive power grid.
Yeah, a whole system that leaps into action in a millisecond.
Exactly. And writing your very first line of computer code is basically exactly like flipping that switch.
It really is. And I love how Aaron Rose captures that exact feeling in the article. He sets this very specific scene to start us off.
Oh, the library scene. I love that part.
Yeah, he drops us right into this grand, totally quiet Victorian library in London. You can picture it, right? Heavy oak tables, dust motes floating in the air, leather-bound books everywhere.
It feels very cinematic.
It does. And it's an environment where, code quality isn't just some boring corporate metric. It's treated as this true, almost ancient craftsmanship.
Yeah, the atmosphere he builds there is just perfect because it sets up the stakes for our two main characters in this scenario. We've got Timothy, who is this junior colleague, and Margaret, who is a senior software engineer.
Right, the veteran.
Yeah, so Timothy is sitting there in the quiet dusk of this imposing library. He's got the glow of his laptop screen on his face, and he's just typed print, open parentheses, quote, hello world, end quote.
The classic first step for any programmer.
Exactly. And he leans back, just completely satisfied with himself, and tells Margaret, it's alive, I understand Python.
He is just so incredibly proud. I mean, he feels like he's totally conquered the machine simply because he made it display some text.
Right. He literally says to her, it displays the text on the screen. It's just text.
Well, Margaret doesn't exactly celebrate with him.
No, she definitely doesn't. She just looks up from this heavy leather-bound ledger she's reading with what the author describes as, and I love this phrase, a gentle, dangerous curiosity.
That's such a great way to put it. Because she points out that while, yeah, he knows how to command the machine to speak, he has absolutely no idea what actually happens after he presses enter.
None at all.
Right. So she walks over, taps the screen right beneath the word print, and she warns him. She basically says, look, to a novice, this is a greeting. But to a specialist, it's a portal.
A portal. I mean, that word completely changes how you look at a basic command.
It really reorients your whole perspective.
Yeah, and that is exactly what we are going to do with you today. We are going to walk through Margaret's portal.
I'm ready.
So let's start right where Timothy's finger is pointing, right at the word print. Because if typing print isn't just magically making words appear on a monitor, what is actually happening there mechanically?
Well, we really have to look at the first section of Margaret's cheat sheet in the article, which he calls the illusion of simplicity. So Python, as a programming language, is designed to be elegant, right? It reads almost like plain English. But to achieve that level of elegance, it basically has to hide a massive amount of C-level complexity.
Wait, okay, so when you say C-level complexity, we're talking about the programming language C, right? Like it's the older one that operates way closer to the actual physical hardware?
Yes, exactly. C is a very rigorous, demanding language.
Yeah.
In C, if you want to store a piece of data, you have to manually ask the computer's memory for space.
Like you have to request it.
Yeah, you have to specify exactly how many bytes you need, and then when you're done with it, you have to manually give that space back to the system.
Wow, so there's no hand-holding.
None. And if you mess up, your program crashes, or worse, it leaks memory. So Python was essentially built on top of C to handle all of those manual, tedious chores for you automatically.
So it's basically just a wrapper. Like Python is secretly doing all the heavy lifting in C behind the scenes so you don't have to.
Precisely. So when you type that print command, you aren't just issuing a direct command to your physical monitor. You are actually invoking this built-in Python function that acts as a gatekeeper.
A gatekeeper.
Yeah, it crosses the boundary from your comfortable high-level Python code all the way down to your computer's operating system.
Okay, wait. So if Python is essentially just walking up to the operating system's border, knocking on the door, and handing off a package, how does the text actually get to the screen? Is Python itself not actually touching the monitor?
Not at all. Not even a little bit.
Really?
Yeah, I mean, Python is a software abstraction. It lives entirely in the realm of pure logic. But displaying text on a monitor, that is a physical reality.
Right. It's actual hardware.
Exactly. You are asking the computer to change the electrical voltage in very specific microscopic pixels on a piece of glass sitting on your desk. Python just flat out doesn't have the authority or the capability to touch hardware like that.
That makes total sense, but I guess I've just never thought about it that way before. It has to delegate the physical labor?
It relies completely on the underlying operating system to do that, whether that's Windows, Mac OS, Linux, whatever. The OS is the only thing that is actually allowed to talk directly to the graphics card and the monitor.
Oh, I see.
So what print does is it takes your data, formats it, and hands it off to a very specific channel inside the OS known as sys.cout, which stands for System Standard Output.
Okay, so print is basically just a delivery person. It packages up the request, walks it over to the sys.stout loading dock, and says, hey, here's the data. Please ask the hardware guys to display this.
That's a great analogy. And even then, it's not like it's instantaneous. Sys.cout often uses something called buffering.
Buffering, like when a video pauses to load?
Similar concept, yeah. It doesn't just immediately send every single individual letter to the screen one by one. That would be wildly inefficient for the computer to process.
Right, that would take forever.
Exactly. So instead, it holds on to the data in this temporary waiting room, that's the buffer, until it gets a specific signal, like a new line character. That signal tells it, okay, the package is totally complete now. Go ahead and send the whole batch to the hardware.
Man, so this simple one-word command is actually this intensely orchestrated handoff between high-level logic, operating system data streams, and physical hardware voltages.
And that is the portal Margaret was talking about. And that's literally just the print command itself. We haven't even talked about what is inside the parentheses yet.
Right, the actual package being delivered, the words, hello world, because Timothy just assumes this is just like raw text floating around inside the machine, right?
Which is exactly where his assumption completely falls apart, because Margaret's ledger goes into the actual anatomy of a string.
Okay, break that down for us.
Well, the text hello world is not raw data. The absolute instant those characters are typed and the program executes, Python constructs a fully formed string ostrich object inside the computer's random access memory, the RAM.
And an object in Python isn't just the literal letters HELLO strung together. It has a whole, like, structure attached to it, doesn't it?
It's a very complex data structure. The moment this string object is born, Python immediately assigns it two incredibly critical attributes.
Okay, what are they?
First, it gets a unique identity number, and second, it gets a reference count.
Okay, let me try to visualize this. Tell me if this worked for you. It's like the string hello world is this newly registered citizen arriving in the computer's memory city.
I like where this is going.
And the second it steps off the boat, it instantly gets a passport. And that passport is its unique identity number, so the city knows exactly who it is and where it is at all times.
I really like the passport analogy, but let's actually push that a bit further. It's not just some static ID badge with a name on it. In Python, that identity number is actually the literal memory address.
A memory address, like a street address.
Yeah, it's the exact geographic coordinate of where that citizen lives inside the actual silicon chips of your RAM.
Oh, wow.
Python needs that coordinate because, as a fundamental rule, Python treats literally everything as an object. It doesn't just see text, it sees a discrete physical entity residing at a very specific address in the memory city.
Okay, so the passport is its physical street address in the RAM city. But what about the second attribute, the reference count? Is that kind of like a popularity score for the citizen?
Actually, a popularity score is a fantastic way to think about it. The reference count is basically this live tracker of how many other parts of your code are currently looking at or relying on that specific hello world object.
So how does that score actually change in practice while the code is running?
Well, let's say you create a variable. You write message equals hello world. The object is created, and your variable message points to it. So the popularity score is now exactly 1.
Makes sense.
But then if you write backup message equals message, now you have 2 different variables pointing to the exact same object. So the score increments up to 2.
Okay, got it.
And Python is constantly tracking this in the background, updating that score millisecond by millisecond as the program runs.
But why? Like, why does Python care how popular the object is? Why go through all that computational effort just to track a score?
Because what we talked about earlier with that C-level complexity.
Mm-hmm.
Remember how in the C language, developers have to manually clean up the memory when they are done with it?
Right, so it doesn't crash.
Exactly.
Yeah.
Well, Python does that cleanup automatically through a brilliant mechanism called garbage collection.
Garbage collection. Okay, I've heard that term thrown around before, but how does the popularity score actually trigger it?
Think of the garbage collector like the city's sanitation department. It is just constantly scanning the memory city looking for trash.
Okay.
If a program finishes running a function or variable is deleted, the reference count for our hello world object drops. And if that popularity score ever hits exactly 0,
It means nobody cares about it anymore.
right, it means no part of your code is using this object anymore.
And so the city just reclaims the apartment.
Immediately, the garbage collector swoops in, evicts the object, and frees up that exact memory address so the operating system can use it for something else.
That is just wild.
It's an incredibly elegant system, right? But it requires this constant, rigorous tracking behind the scenes to work.
Right. It's doing all of that, assigning physical coordinates, constantly incrementing and decrementing popularity scores, checking for zero all in split seconds before the words even make it to the physical screen.
Yeah, we are deep inside the hidden machinery now.
We really are. So, okay, we know print is the gatekeeper managing the buffer and the OS handoff. And we know Hello World is this newly minted citizen with a physical address and a dynamically tracked popularity score.
Yep.
So the next thing Margaret's ledger addresses is the actual geography of the city itself. Like, where in the RAM does the citizen actually live?
And this is a super crucial section of the article. Margaret introduces Timothy to a really vital physical boundary inside the computer's memory. The RAM is basically divided into 2 distinct regions. They're called the stack and the heap.
The stack and the heap. Okay, it sounds a little bit abstract. What is the fundamental difference between the two?
It all comes down to how memory is organized and how it's accessed. So let's start with the stack. The article describes this thing called an active execution pointer.
Okay, what's that?
Think of it like a spotlight that is tracking the exact line of code that is currently running at any given microsecond.
Like reading along with your finger in a book.
Exactly. This pointer moves incredibly fast, and it lives on the stack. Because the stack is highly, highly organized. It operates on a strict last in, first out principle.
Oh, like a stack of plates at a buffet. You can really only easily take the top one off or put a new one right on top of the pile.
Yes, perfect analogy. It's rigid, it's predictable, and because of that, it is extremely fast. It stores the active frames of your functions and the pointers, which are just the references to your data, but it does not store the heavy data itself.
Okay, which means our Hello World object isn't actually on the stack.
Correct. The newly created string object with its passport and its popularity score is carved directly into the heap.
Okay, let's try to map this out visually for everyone listening. If the stack is really fast and organized, is it helpful to think of it kind of like a busy chef's cutting board?
Oh, I like that.
Right, like it's where the active, fast-paced chopping happens. The knife is the execution pointer, just rapidly moving from task to task, slicing things up.
I really like that visual. The cutting board is the immediate, fast workspace.
Yeah.
And so following that exact logic, the heap would be the giant walk-in pantry in the back of the kitchen.
The pantry, where all the actual heavy ingredients are stored.
Yes, because the heap is vast. And unlike that perfectly organized stack of plates on the cutting board, the heap is dynamic and relatively unstructured.
Right, it's just big shelves.
Exactly. When Python needs to create that Hello World object, it basically rummages through the heap, finds a chunk of free space on a shelf that's big enough, and carves it out for the object.
So the chef isn't keeping, like, the giant 50-pound bag of flour right there on the small cutting board. They leave it in the pantry. But wait, how does the chef actually know where to find the flour when they need it quickly?
Ah, that is where they use the passport, the memory address we talked about.
Oh.
Yeah. On the cutting board, which is, the stack Python keeps a tiny, lightweight little slip of paper with the exact address of where the heavy object lives back in the pantry of the heap.
So the variable that we actually type in our code, like the word message, is literally just that slip of paper sitting on the cutting board. It's just a
Yeah.
pointer.
Yes.
The actual heavy data is sitting way out in the pantry.
You've completely got it. And Margaret specifically notes in her ledger that understanding this exact boundary, the literal distance between the cutting board and the pantry, is the defining difference between writing code that just sort of merely works and writing code that actually scales up to professional levels.
Well, let's dig into that actually, because why does the geography of where these things live matter so much mechanically? Like, if the computer is doing it all at lightning speed anyway, why on earth does the developer need to care about the cutting board and the pantry?
Because traversing that boundary carries a real computational cost every single time.
What do you mean?
Well, accessing the pantry takes a very different kind of effort than simply moving a knife around on the cutting board. When your program creates an object in the heap, the system has to spend processing time searching for available space. It has to allocate it.
Right.
And then every single time you want to use that object, the execution pointer on the stack has to look up the address, walk back to the heap, and fetch the data.
It has to literally walk back to the pantry every time.
Yes. And if your code is inefficient-like, if it's constantly running back and forth to the pantry for every single tiny ingredient instead of batching the requests or reusing items, your kitchen is going to completely grind to a halt.
Which I guess brings us to the ultimate question of this whole deep dive.
Yeah.
We have this beautiful Victorian library. We have Margaret dropping this incredibly intense knowledge on Timothy about sea-level wrappers, garbage collection, and the stack versus the heap. It's an amazing mechanical breakdown. But why did Margaret hand Timothy a brand new, fresh notebook and tell him his journey was basically just beginning?
Well, it really comes down to the defining traits of a master developer, what the article calls a specialist. Margaret explains that a novice just memorizes syntax.
Right, they learn what to type.
Exactly. They learn how to write the basic commands to make the machine do the thing. But a specialist tracks resources.
Tracking resources, meaning they are actively, consciously aware of what they were putting in the pantry.
Exactly. Because understanding how Python allocates these objects is absolutely crucial for the long-term health and stability of your software. If you don't understand the reference count, that popularity score, you can very easily write code that accidentally keeps a reference to an object forever.
Oh. And if the score never hits zero?
The garbage collector never cleans it up.
Right. So the object just sits there indefinitely, taking up permanent space in the RAM. And if your code does this in a loop, repeating, thousands of times a second,
Your pantry is going to fill up with rotting ingredients until there's literally no physical memory space left anywhere.
and that is a memory leak? I've heard that term. The program just crashes because the city is completely full?
Yes, it's one of the absolute most common and devastating bugs in software engineering. Knowing exactly how Python handles objects is what prevents those leaks. It also allows for optimizing variable reuse.
Oh, so.
Well, if you know how the heap works, you can purposefully structure your code to reuse an ingredient you already brought to the cutting board instead of forcing the system to carve out brand new space in the pantry every single time.
Okay, that makes so much sense. The article also mentions that this knowledge sets the stage for understanding deep versus shallow tracking.
Yeah, that's a big one.
What does that actually mean in the context of our kitchen analogy?
It's all about how you copy things in your code. So if you do what's called a shallow copy, you are basically just writing out a second little slip of paper on the cutting board that points to the exact same bag of flour in the pantry,
Okay, so both variables are modifying the exact same physical object.
which could be super dangerous if you thought you were modifying a safe backup.
Oh yeah, you'd be ruining your original data.
Exactly. Now, a deep copy actually goes all the way into the pantry, buys a second completely independent bag of flour, and puts it in a brand new spot on the shelf.
But I'm guessing creating a deep copy takes way more time and memory to do.
Way more. And the point is, you can't make informed professional decisions about which one to use unless you understand that the stack and the heap exist in the first place.
But wait, I have to play devil's advocate here for you listening, because if I am just a casual scripter, like maybe I'm a marketer automating some boring spreadsheets, or a researcher just doing a little data analysis, isn't Python's whole selling point that I can just completely ignore all of this?
It is, yeah.
Right, because we established earlier that Python was specifically built to hide this exact C-level memory management, so developers don't have to stress about pointers and garbage collection. If my text prints on the screen, why do I actually need Margaret's fresh notebook?
Look, it's honestly the most common trap in all of programming. Yes, Python abstracts all of this away to make your life easier. It is a totally brilliant feature of the language because it lowers the barrier to entry.
Right, anyone can start coding.
Exactly. It allows beginners to build really useful tools incredibly fast. But, and this is a big, but remaining willfully ignorant of the underlying machinery, puts a hard, fast ceiling on your abilities as a developer.
A hard ceiling on what you can build.
More on how your builds will actually perform in the real world. When your small script suddenly needs to process 1,000,000 rows of data instead of 100, or when your little prototype web application suddenly gets 10,000 users hitting it at the exact same time, the illusion of simplicity totally shatters.
Yeah, because the machine actually has to do the physical work eventually, and if you've been inefficient, it just bottlenecks.
Completely. If you don't respect the hidden world, if you just treat the heap like this infinite magic box, your ignorance leads to bloated, slow code that just falls apart under any real pressure.
Wow.
You can stay a novice forever, and your code will work perfectly in a vacuum, but it simply won't scale.
It's kind of the difference between, like, knowing how to drive a car to the grocery store and being a mechanic who understands fuel injection well enough to rebuild the engine for an actual race.
That's a perfect way to summarize exactly what Margaret is trying to teach Timothy. To become a specialist, you have to pull back the curtain. You just have to respect the infrastructure. Because ultimately, knowledge of how the machine actually breathes and moves is what leads to real mastery.
Man, let's just look back at the incredible journey we've just taken, starting from just two simple words. Hello, world. We really did walk right through Margaret's portal today.
We covered a massive amount of invisible architecture, for sure.
We really did. We started with the gatekeeper. We saw how print isn't just making letters appear, it's actively managing C-level complexity, acting as this bridge to package data and hand it off to the operating system's sys.stateout buffer.
Which then has to negotiate with the actual physical hardware.
Right. And then we examined the package itself. We realized Hello World is actually this complex string data structure, complete with its own memory address coordinate and a live tracked reference count.
A popularity score that literally summons the garbage collector the second it drops to zero.
Exactly. And then we mapped the physical geography of the RAM. We explored the lightning-fast cutting board of the stack where the execution pointer lives, and the vast, demanding pantry of the heap where our string object actually resides.
And finally, we uncovered the why behind all of it. We learned that to move from a novice to a specialist, you basically have to understand this architecture so you can track resources, optimize that stack-to-heap boundary, and prevent those catastrophic memory leaks as your applications scale up.
Margaret's lesson in that Victorian library really is profound. Nothing in the digital world is ever just text.
Never.
The illusion of simplicity is just that. It's an illusion designed to make us feel comfortable while the machine is doing literally millions of microscopic calculations every single second.
That actually leads to a final thought that I think is really worth exploring long after this deep dive ends today.
Oh, what's that?
Well, we just spent all this time deconstructing the absolute simplest program a human being can write. A basic greeting. And we saw that even Hello World spins up this intricately choreographed dance of memory allocation, heap carving, live reference tracking, and operating system handoffs.
Right, all of that just to put a few tiny pixels on a screen.
Right. So I want you to scale that up in your mind. Just imagine what kind of sprawling astronomical universe of creation and destruction is being spun up, tracked, and torn down by the garbage collector every single second when you run a highly complex machine learning algorithm.
Oh, wow.
Or when you load up a massive interactive web application with thousands of users.
Just millions and millions of citizens in that memory city constantly moving, appearing, and being evicted at the speed of light.
The scale is almost terrifying to think about, honestly. But the crazy part is, all of it, even the absolute most advanced AI on the planet right now, relies on the exact same fundamental mechanical truth we explored today.
The stack, the heap, the reference counts.
It's all there. It's the exact same foundation.
That really does make you look at your computer totally differently. It's like standing in that dark room, your hand resting on the light switch, and suddenly realizing you can actually feel the hum of the entire electrical grid vibrating right through the wall.
Yeah. You'll truly never look at a simple line of code the same way again.